Okay, so I still haven't given a definition of genuine G-spectra, except for in the CP case. But I want to move now into the norm and use that to motivate the definition a little bit. And just as a reminder, last week I gave this kind of, idea of a definition of the norm where, if I think about inducing a representation V from a subgroup H, then, V has an H action, and I somehow combine the H action on V with the G mod H action on G mod H to give a G action on the G mod H fold direct sum of V with itself. And the norm is the same thing, but with the tensor product. Okay, so it's like this monoidal induction functor. And let me first now give you some instances of that. And let's start just in G spaces. So here it's really easy. In G spaces, the tensor product is the Cartesian product. It's a Cartesian category. And so the norm coincides with co-induction, which is to say it's just the right adjoint to restriction. Okay, so that's using the Cartesian monoidal property here. And so just to draw that in a diagram, let's look at Borel spaces, for example. Then I have this restriction functor res GH induced by the inclusion of H into G. And the norm is just the right adjoint in this category. So that right adjoint implements this construction because it's Cartesian. Okay, and the same thing goes for genuine G spaces because it's this functor category. Okay, and for Borel and naive G spectra, I'll just put it here. This gives a straightforward definition of the norm in the stable category. So I'll just give you the Borel version of that. So if I take Borel pointed spaces, then I have this norm here, which was just an adjoint. And I can go now to the stabilization of that, which was Borel G spectra. And I can do the same thing here. And because this functor here commutes with filtered colimits, and I get this from this by inverting the sphere S1, there is a functor making this diagram commute that also commutes with filtered colimits. Shifted, yeah, right, thank you. Okay, so that's sort of easy in this case because, well, these versions like the Borel G spectra or naive G spectra were again just functor categories. Okay, and well, I mean the definition we will give in the genuine case is actually kind of the same, but just to give you a sense for what extra information the genuine category is carrying when it comes to the norm. I want to point out a nice connection with the Nicolaus-Schulze-Tate diagonal. So the Nicolaus-Schulze-Tate diagonal is equivalent data to the Hill-Hopkins-Ravenel norm functor from spectra to CP spectra. And that comes through this Tate squares perspective. So if I look at the Tate square of the norm, it looks like this. Okay, and we will see in a moment that taking the norm followed by the geometric fixed points in this case is just the identity functor. And so, well, the point is I can go between this. So if I give myself the HHR norm, then I have this functor and a corresponding Tate square. And the map on the right-hand side is this Nikolaus-Schulze Tate diagonal. On the other hand, if I think of genuine CP spectra as being defined by this pullback square, then I can use this natural transformation here to define the norm functor from spectra to CP spectra in this way. Okay, so these are equivalent data, and it's again telling us that, you know, well, this genuine category has a really nice connection with this Tate construction. Okay, so now let me give a definition of genuine G-spectra. So I get genuine G-spectra by taking genuine G spaces and inverting representation spheres. So I have a finite group. That means I just have to invert the regular representation. And I think probably a lot of folks are familiar with this, but there's this paper of Roballo where he explains how to invert symmetric objects and make sense of this expression of inverting this representation sphere. But anyway, it can be done and has nice universal properties. Let me write those now. So the first one is, well, there's this suspension spectrum functor that goes from, so this is my notation now for this genuine G spaces category, this SG plus. It goes from there into this inverted, this localized category. And this arrow is initial in symmetric monoidal presentable infinity categories, inverting S rho. Okay, and that theorem can be found in this paper of Roballo. And there's also a slight variant of this due to Bachmann-Hoywa, where they say it's also the initial arrow in the same arrow. Initial arrow that's a filtered, sorry, I need to say sifted, I guess. Sifted colimit preserving functor like this, inverting this representation sphere where D is, well, at the very least, a symmetric monoidal infinity category where the tensor product commutes with colimits in both variables. And the reason that we want to point out this second version is because, well, this norm functor, even on G spaces level, doesn't preserve colimits, so it's not a left adjoint. But it does preserve sifted colimits, and so it is enough by this second universal property to define the Hill-Hopkins Ravenel norm. Yes, yes. Colimit preserving symmetric monoidal. Yeah, thanks. Yeah, because we want to apply this to the norm functor, which I will. Actually, let me just write the next thing, and then I will explain it from there. So I want to use this second universal property to construct the HHR norm, and I just mimic the construction of this Borel norm. Anyway, I use the spaces norm, which is just this right adjoint here, and then I check that it preserves sifted colimits. And the point is, it doesn't preserve all, I mean, it's not like it doesn't preserve cofiber sequences, for example. So that's a really important, property that this doesn't have. And I mean, you can see that just like on the underlying level, when you take the tensor square of something, that doesn't preserve cofiber sequences. Okay, but it preserves shifted colimits, and so it's enough to define this functor here, and that's the Hill-Hopkins Ravenel norm. Okay. The geometric fixed points functor, I already gave you a definition in terms of this cofiber sequence and the genuine fixed points, but let me also just say that you can define this in the same way using, well, a functor out of G spaces, namely evaluation at G mod G, which is, in this model of G spaces, the fixed point space functor. So that functor, well, is a colimit preserving. It's a left adjoint, and in particular, it defines the geometric fixed points functor in the same way. Okay. Let me give you a couple more definitions. So first I want to define the inflation functor from spectra to G-spectra, and this is just the unique symmetric monoidal colimit preserving functor from spectra to G-spectra. And the reason I want to define that is so that I can define its right adjoint. And that's the genuine fixed points functor, which I've already talked a lot about, but now we have a definition. And one nice thing you notice about it right away is that it preserves colimits itself because the inflation functor preserves compact objects. And so that's sort of what goes into this Adams isomorphism claim as well, and I'll explain that more in a second. But this genuine fixed points functor is much better behaved than, for example, the homotopy fixed points functor because, for example, it preserves colimits. Okay. So that will be our definition for now of genuine G-spectra and all these functors. And now I just want to kind of give you some ways of thinking about genuine G-spectra. So I want to state the following are equivalent, but I'm not really stating anything that amounts to some precise theorem statement. I just want to explain roughly how you go between the different ideas of genuine. So don't expect this to be so precise. So I want to state some properties that can be thought of as the genuine properties, so the difference between this category and the naive G-spectra category, for example, and explain how to go between them. So the first one is the one we use to define it, which is that the representation spheres are invertible, which I want to think of as like G stability. Second one is that there are transfer maps in G-spectra, which is, well, what you would mean by modeling G-spectra as spectral Mackey functors. The third is the fact that orbits are self-dual in G-spectra, which is the same thing as the Wirth-Muller isomorphisms, which I would also like to call G semi-additivity. And the fourth is this Adams isomorphism, which, as I said before, is corresponding to this Tate squares point of view, where you have these pullback squares and a strong connection to the Hopkins-Lurie Tate construction. Okay, so I want to give some just ideas on how to go between these concepts. And I'm going to do my favorite thing, which is just to work in C2 spectra, and there's enough going on to sort of see what's happening, and you can make these ideas work more generally. Okay, so let's go from invertible representation spheres to the existence of transfer maps. So first of all, if I look at the orbit C2 plus, then there is an equivariant map from C2 plus to the sphere, just in C2 spaces even. And that's just, of course, the quotient map. And the transfer map in C2 spectra is some map going the other way. And it's something interesting because, well, it can't exist stably. It can't exist on the space level because the left-hand side is fixed, the right-hand side is free. And you can even show that in this stabilization category, this naive G-spectra category, that there won't be any non-trivial maps like this. Okay, but when you allow yourself to invert representation spheres, you get something non-trivial and interesting. So I want to call this transfer. Okay, and well, the idea is if we can invert a representation sphere, then we can produce this map after suspending by a representation sphere. So let's suspend by the sign sphere, so the one-point compactification of the sign representation of C2. And since C2 plus is a free thing, when I smash with something, it frees up the action. So this is the same thing as a C2 plus smash S1. Okay, that's not so hard to see. And you obtain this map via the Pontryagin-Thom collapse provided by the embedding, equivariant embedding of a C2 cross D1 into sigma. So in the sign representation, you have your plus or minus 1, and you can take little neighborhoods around them, little D1 neighborhoods to produce an equivariant embedding like this. And this Pontryagin-Thom construction is the statement that you have a contravariant functor given by one-point compactification with respect to open inclusions. So I collapse the complement, and I get this collapse map going back the other way. So from the one-point compactification of this, which is S sigma, to the one-point compactification of this, which is C2 plus smash S1. Okay, and I only had this after suspending by the sign representation. And when I take that map in G-spectra and I now desuspend it, I get this transfer map. Okay, so that's kind of nice, just coming from this geometric construction. And this also corresponds to this spectral Mackey functor perspective in the following way. If I have a genuine C2 spectra, then I have already defined these genuine fixed points, but they're also they can also be viewed as a part of this Mackey functor perspective in the following way. So first of all, I can rewrite x as the internal Hom from the unit to x, and then I can use this transfer map that we just discussed. So first of all, I have the underlying spectrum of x as the C2 fixed points of this internal Hom from C2 plus, and this comes from the fact that C2 plus is just the induced sphere from the trivial group to C2, where this induction is the left adjoint to the restriction from C2 spectra to spectra. Okay, and I have my two maps. Let's call this one res, and this one transfer. And then I have the action of C2 on itself acting on this, producing the action on the underlying spectrum. And this diagram is this spectral Mackey functor for a C2 spectrum. Okay, but anyway, the structure maps in it are coming from this geometric construction. Okay, and yeah, let me just say, upgrading this into an actual categorical description of genuine G-spectra is due to Clark-Barwick. Okay, let's go from now 2 to 3. Oh, sorry. Yeah, thanks. Okay, let's go from 2 to 3 now, and the point here is that once I have G-spectra expressed as some category of Mackey functors, which is to say I can write it in the following way. I have a description of genuine G-spectra as product-preserving functors from the span category of finite G-sets into the category of spectra. And this span category is, well, if I have, say, two orbits, G mod H and G mod K, then the maps between them are diagrams like this, where T is some other finite G-set T. That's what morphism in this category is. And the point is that, well, I can get this, I'm going from 2 to 3, so I want to show you that the orbits are self-dual. So the point is just that, well, the suspension spectrum of an orbit as a genuine G-spectrum from this point of view is the same thing as the sort of Yoneda object on the orbit G mod H from the point of view of this as a functor category. And the orbits are just manifestly self-dual in this span category because the mapping spaces themselves are symmetric. Okay, so this self-duality comes for free from this spectral Mackey functors perspective. So just to be clear, what I'm saying is that there's an equivalence of G-spectra from an orbit to its dual in G-spectra. Okay. Now I have a couple more steps to go in this. Yeah, okay. Are there any questions? Yeah.
Just to be pedantic.
Yeah.
I think to get the actual spectral Mackey functors formula, don't you input the Tate splitting, which uses the atom isomorphism?
Let me see.
Or you use atom isomorphism?
Sorry, which step are you at?
I think, well, from the existence of transfers,
Yeah.
to get to the actual spectral Mackey functor equivalence of categories, I think you need the atom isomorphism in some step, right?
I think you need properties of these transfers.
Okay.
Right, so maybe the way I've said it is a little bit inaccurate. Let me just keep it at a not very precise level, and I guess what I've really shown you is how to go from spectral Mackey functors to self-duality of the orbits. But yeah, you're right. You don't just get this categorical description from the existence of some family of transfer maps. They have to satisfy properties. Okay, let's do 3 to 4. So this one's kind of interesting. So the atoms isomorphism is a bit strange at first glance. So state it again. It says when you take the G spectrum X and you take the genuine fixed points of this, that you get the homotopy orbits. And the idea about this following from the G semi-additivity is as follows, and this perspective is in this recent paper of Knossen, Lentz, Minskins, which is, well, about the Adams isomorphism. And I guess at a really high level, the idea is something like both sides commute with colimits in X, because I have the genuine fixed points here and I have a left adjoint here. And if I plug in G plus to both sides, I get the following correspondence. So if I take the, let's do the right-hand side first. If I take the homotopy orbits of G plus, this is again the induced sphere. I can show that this is just the sphere because it's a composition of left adjoints. I can check what that is. On the other side, if I take this, then, well, this is the same thing as G plus genuine fixed points. And by the self-duality, this is the same thing as the fixed points of the dual. And then I again use that this is just the induced sphere to reduce this to the sphere by that adjunction. Okay, so now that I have that these both agree on G plus and preserve colimits, I would be done if I had a map between these. And that's the tricky part of it. But let me just say that you can construct this map using the Hopkins-Lawson map. And I won't explain how to do that, but that's possible. And all you're using then at the end of the day is this Wirth-Muller isomorphism.
Sorry, so G plus is, so you reduce the free case first because you take the free case anyway.
Exactly, yeah. So here I can assume, in both cases, I can assume that X is written as a colimit of G plus of free spaces. And so I just need to check on the sort of generator once I have a map.
You said Hopkins also. Do you mean Hopkins-Lurie?
I meant Hopkins-Lurie, thank you. Yikes. Okay, let me give you two more directions of this equivalence here. These are a bit quicker. Let me show you that 4 implies 2. Well, let me just at least show you how to get transfer maps using the Adams isomorphism. So if I have the Adams isomorphism, oops, I claim I can construct this weird map from the sphere to C2 plus, and I do that in the following way. So first I just write the sphere, let's do the C2 thing again, as the homotopy orbits of C2 plus, that was just this part here. And then we use the Adams isomorphism to write that as the fixed points of this. Which is the same as just C2. And then I use the fact that this genuine fixed points is the right adjoint to the inflation functor to produce a map from the inflation of the sphere to C2 plus in C2 spectra. And the inflation of the sphere is the sphere.
So isn't it somewhat easier to do the Adams isomorphism because producing a transfer is literally producing a fixed point of C2? I mean, like a multiple class from sphere to C2 plus is literally an equivariant fixed point.
Yeah.
And the equivariant fixed point set is just by the Adams isomorphism, no multiple fixed points of C2, but this is then just.
Isn't that what?
This is what you did? I'm sorry.
No, it's, yeah.
Sorry.
I agree. It's easy. Yeah.
I got confused by the EC2 and stuff. Sorry.
Yeah. I would just wanted to be super explicit there, but yeah, it's exactly what you said. Okay. Let me give one more step, which I think is one of the more interesting ones. How do you go from the transfer maps? Oh, sorry. I am going not from 2 to 1 now, but from 3 to 1. I think that still forms a circle. Okay, so let's assume that the orbits are dualizable. well, let's assume that they're self-dual, in particular dualizable, then this implies that representation spheres are dualizable. Because I can write down a finite GCW complex structure on these. I can write them as a colimit of things built out of finitely many G orbits. And once I know that this is dualizable, I can check that it's invertible on geometric fixed points. So I have these geometric fixed points which are symmetric monoidal jointly conservative functors. And I can just look at the, at the map which asks, I can look at the map that's defined by the dual of SV to the sphere to check that, SV tensor its dual is the sphere, and I can check that that's an equivalence on geometric fixed points. And we define the geometric fixed points so that it takes the suspension spectrum of a space and gives me the suspension spectrum of its fixed point space, which in the representation sphere context corresponds to this. And really the dimension of that as a non-equivariant thing. And that's invertible, so we know then that the representation sphere is invertible. Okay, but you needed to know that SV is dualizable to make this argument. And that isn't true in the naive G-spectra category. And actually, if it were true, you would also be able to show that the orbits are self-dual, that the orbits are dualizable. And that's the problem in this naive spectra category, is that the orbits themselves are not dualizable. Okay, and yeah. So then all of these properties aren't going to hold for it. Okay, that's all I want to say about all of these genuine properties. Yeah, any questions on that? Okay, so let me more or less finish things off by explaining now how this all fits into this picture of G categories. So I guess maybe one way of thinking about what I'm going to say now is that if I look at these genuine properties here, there were these ones that I put in quotes like G stability and G semi-additivity. And the idea with G categories is that there ought to be some framework in which these are just the native notions of stability and semi-additivity, for example. And well, that is what leads you to this. And a lot of this is based on some conjectures of Mike Hill. And let me just give you the basic definition. So a G category is a functor from the orbit category to categories. Okay, and I think, well, the thesis of J. Shah is where this kind of thing really first appeared in full, as far as I understand, and also with corresponding study of notion of colimits and that sort of thing for a G category. Okay, and also having these native notions of G things gives us a lot of interesting information about symmetric monoidal structures. So let me state what the native notion there of a symmetric monoidal category is. So this is a product preserving functor again from this span category to categories. So this is in other words, like a Mackey functor of categories. This definition is due to Nard and Shaw. Okay, and well, I'm going to go through a bunch of this stuff very quickly, but I just want to really focus now on this symmetric monoidal stuff here. So this sort of gives another point of view on how to construct the Hill-Hopkins Ravenel norm, namely that should be a part of the G-symmetric monoidal structure, the sort of native symmetric monoidal structure in this context, and that on G-spectra should be something which just comes from a universal property like the symmetric monoidal structure on spectra. So let me now state a theorem which I hope I state correctly. So there are G-symmetric monoidal categories. PRL, PRL stable, and because they're G categories, I'm supposed to underline them instead of putting the G implicitly in the notation, but this is all happening in some G world. And these have units, category of G spaces and category of G spectra, respectively. Okay, so let me just attribute this to some people. So first of all, I think this first appears in Nardin's thesis. You can read a lot about this also in Keif's thesis, so Keif-Hillman. And then you can correct me if I'm wrong, Branko, but I think this is also to appear in forthcoming work of Branko Juran and Natalie Stewart.
This is also in
Yeah, maybe also put,
Sorry?
maybe you should just put the entire working group here. Like Emma, Toby, whatever.
Why not put the same Knossen wins?
But the
No,
whole
no,
stuff
that was
really,
really Knoss and Holzing, that's.
I think mostly this is, I think, like really in a fully correct way, this is not really anywhere, right? Currently.
Because you want norms also.
Hmm? Yeah, I think it won't just not be anywhere.
Okay. This should be a true theorem at someday. Well, anyway, yeah, my point is that, like Lurie's construction of the symmetric monoidal structure on the infinity category of spectra was to, put a symmetric monoidal structure on PRL stable and see that it's the unit there, so that it's an algebra in that category. And the same thing can be done here, and sort of carried along with this in this G-symmetric monoidality are these HHR norms. Okay, so it sort of also satisfies a universal property. Okay, I guess. Yeah, that's also complicated, and I think that's the part that Keif did a lot of work on. Please correct me if I'm wrong, but I think Keif has a paper called Parametrized Presentability, and yeah, my understanding that he worked on that a lot. Okay. Let's put this here. Yeah, so I mean, I guess there's a notion of G colimit, and the presentability is sort of the one corresponding to that.
It's like the end of something is not the hard part to say, so it's the colon.
Sorry?
He said that like phrasing these G columns is a bit of a difficult thing to say.
Yeah.
Like presentability usually is like if it's in kappa of something and it has all columns, it's the in kappa part not hard to say.
I don't know. Maybe somebody can help.
I mean, it's all the same in the end, as in the non-parameterized. I mean, I think it turns out that you can just ask for parameterized co-complete and point-wise accessible.
And all, I mean, the factoring also gives, yeah.
But isn't that included in co-complete?
It means that one has to have left and No, I want the, so the factor from the orbit category, this is the PRL, the thing which defines your presentable category. I think, and you want it to be autocomplete.
I thought it's enough to ask for co-complete as a G category and point-wise presentable.
I also thought so.
Maybe it's,
I think the co-completion translates to some.
but it's also, I mean, you can also characterize it as a localization, an accessible localization of the attribute.
Sorry. No worries, no worries. Yeah, so these things are subtle, I guess. Okay, so let me just make a remark. So I guess arguably one of the most interesting things about this extra structure of G-symmetric monoidality is then the corresponding native notion of commutative monoid. And I'm not going to define what that is, but it pops out of this theory. And so for a G-symmetric monoidal category C underline, you're going to have some category of G-commutative monoids. And in particular, the norm satisfies a nice universal property with respect to these. So there's some restriction map, a forgetful functor from G-commutative monoids to H-commutative monoids in C, usual restriction functor. And the left adjoint to this is the norm. So for example, if I have a G-commutative monoid in G-spectra, then it's going to be some E-infinity ring in G-spectra that's also equipped with a map of E-infinity rings like this. This is the co-unit of that adjunction. Okay, and well, this is a very important piece of structure for us. If you want to sort of unravel this and think about this in the category of CP spectra, I would take a look at this paper of Lucy Yang, where she sort of gives a diagrammatic description of this CP commutative monoid category in terms of the Tate square. Okay, so things like that can be done, but anyway, I want to focus on this piece of structure. And I want to apply it to, well, the examples that we've seen so far, namely Borel E-infinity rings. And this is a theorem of Blumberg and Hill that Keif-Hillman proved in a much more general context as well, which says that Borel commutative rings are G commutative rings. So I could state this much more precisely, but I won't for now. Let me just say that if you take a E-infinity ring with a G action and you regard it as a Borel G spectrum, it has a canonical G commutative monoid structure. So in particular, our Morava E theories are going to have this property as G spectra. Okay. Let me finish off in the last 5 minutes by sort of tying this story back to where it started, namely with this connective models thing. So let me give you a definition of MUR. So this is defined by Fuji and Landweber. And well, it's the spectrum MUR. It's the spectrum MU with the C2 action by complex conjugation. So slightly more precisely, if I think about MU written as a sequential spectrum, I get it in the following way. I can take these Thom spaces of universal bundles over BUN and put these together to form this Thom spectrum. And then I can notice that everything had a C2 action on it on the space level in terms of complex conjugation, and that all of the structure maps are equivariant to that with respect to that, where this minus 2n becomes minus n rho, where rho is the regular representation, and I have these complex conjugation action maps on these Thom spaces. Okay, so well, let me state now a nice theorem of Hill, Hopkins, Ravenel on these, which is based on a construction of MU due to Schrader. And the theorem states that MUR, well, this spectrum admits the structure of a C2 commutative monoid in C2 spectra. Okay, and well, in general, sort of things that come from geometry in a nice way like this often admit the structure. And there is a way to prove this theorem purely in terms of some sort of J homomorphism construction of MUR. And I don't have time to say much about that other than in upcoming work of Emma Brink and Tobias Lenz. They construct a G commutative, so they construct a J homomorphism equivariantly that is a morphism of G commutative monoids in spaces, and you can form MUR as a Thom spectrum in that sense, and get that it has this nice commutative structure, for free from that in the usual sort of idea of a Thom spectrum as a colimit. Okay. Two more things I need to state before we can get to the punchline here. So I want to state the following theorem of Han and Shi. This says there is a C2 equivariant homotopy ring map from MUR to EN. So every Morava stabilizer group at the prime 2 has a C2 subgroup given by the formal inversion on the formal Lie group. And that is the C2 subgroup of these C8 subgroups that we are interested in. In particular, this has a C2 action via that, and that this map is a C2 equivariant ring map. It's also recently by Ryan Quinn and Chi Zhu shown that it lifts to an E-row map, so some equivariant version of an E2 map. Okay, but the sort of upshot is that now I can apply the norm functor to this. And use that this Borel thing is a C2 to the n commutative monoid to construct a C2 to the n equivariant map like this. So let me put n's here in the right spot. Here I really want to take our n's to be the 2 to the n minus 1, where we have the C2 to the n subgroup in the Morava stabilizer group. Okay, so this is for any m, let's say. Okay, and well, just let me state a couple of last points and then I'll be done. So the sort of upshot of having this is, first of all, that the geometric fixed points of these norms, let's say, just going to write of these norms, is easy to compute because the geometric fixed points of MUR is MO, more or less by definition of this Thom spectrum and the way that geometric fixed points interacts with suspension spectra. Okay. On the other hand, the geometric fixed points of this Borel thing is the Tate construction, and that always vanishes. So there's sort of no interesting information to be gotten from the geometric fixed points functor from this Borel spectrum. So its geometric fixed points vanish. And that prevents you from making a lot of the sort of nice induction arguments that we will make on the left-hand side instead. Okay, and the sort of punchline of the talk then is that our E4, our connective model equivariantly, which is supposed to be this sort of sim-M construction, will be a quotient of this norm. So I'm going to basically take things in the kernel of this map and mod out by them equivariantly in the source, and that's going to build this E4 connective model for me. And just as a reminder, I told you how this works for real K-theory, where you can sort of build K-theory as a quotient of MU, and you can do that equivariantly, so you can do it as a quotient of MUR. And yeah, again, this is by work of Krish. And this construction of E4, this HHR construction, is again really just kind of the same idea, but just using this norm functor to get up to the C2 to the n category. And yeah, this will be a very similar construction to that. Okay, stop there.